Okay, hi everybody. We're going to get started here. This is an extended session with both an intro and deep dive to running IoT and Edge applications utilizing Kubernetes. We've got 4 speakers here from different regions of the world. I think we're standing up so you can see who they are, but Cindy, why don't you introduce yourself just briefly?
Okay, my name is Cindy Xing. I'm a software architect at FutureWay. So I help FutureWay to build the public cloud infrastructure, specializing in IoT edge computing. Currently, I'm leading the open source project called the KubeEdge, and also I'm co-chairing with this gentleman for the Kubernetes IoT Edge work group. So before FutureWay, I worked in Microsoft for over 12 years, have a lot of experiences in building distributed system.
Hey, so my name is Dejan. I'm a software engineer with Red Hat, working in the messaging and IoT team. At Red Hat, primarily working within the Eclipse IoT working group on a couple of interesting projects. One of the most notable is the cloud scale messaging for the IoT. Also, yeah, last year we started the Edge working group and IoT Edge working group within the Kubernetes community to try to explore this topic a little bit further.
Steve Wong, I'm a software engineer with VMware, and I'm assigned to work on Kubernetes and a few other open source projects, and lead of the IoT and Edge working group. In a former job, I was on the founding engineering team of Wonderware, which was in the IoT space before they called it IoT. Kilton?
Cool. Hi, I'm Kilton Hopkins. I'm a software engineer and architect and co-founder of and CEO of a company called Edgeworx, which is an edge computing company. And I'm the original designer of the Eclipse IOFog open source edge computing layer, and we at Edgeworx are still the core maintainers of that. And so that's part of the Eclipse Foundation's Eclipse IoT and Edge division. So.
Okay, thanks. Let's get started with the deck. Okay. This is the agenda. I think you'll learn the agenda as you watch. So let's just skip this. Cindy?
Yeah. So let's talk about the use cases. I think most of you has the idea of the benefits of edge computing. Then if we look at all the common use cases, probably we can summarize in the following. For example, you might have a lot of IoT devices and at the edge. And then somewhere you want to have a gateway to manage all the devices. The benefit you can gain from it is mostly the low network latency, and then you can remotely manage a fleet of devices. Then the other would be, like, say, for example, you're doing artificial intelligence at the edge. For example, you have a machine manufacturer, and then currently a lot of companies are using OPC UA to do the data collection using time series DB, and then you want to have the data to be locally analyzed and then upload some of the data to the remote. So in that sense, you want to remotely manage your data and also have the data uploaded to the cloud, and then you have aggregated analysis further. So from a requirement perspective, we would say, you see, like, I want to remote manage my nodes or resources. I want to remotely deploy or orchestrate my applications, and also consider, because I have a fleet of edge nodes, the scalability can be huge. And then the fourth one would be the network connectivity between the edge node and the cloud might not be reliable. That's the challenge and the fact. So based on that, let's talk about what kind of approaches are available. So the below are the ones the working group we summarize and come up with. So you can, actually we have a white paper published in our IoT working group. You can go there and read more details. So in summary, if you look at this architectural chart, the edge node can be categorized in 2 buckets. One, we call it infrastructure edge. For the infrastructure edge, most likely you're going to run a whole cluster at that point. And then your IT admin or user can just talk to your infrastructure edge and then scheduling your application or manage your resources. Then the other type of edge, we call it device edge. Basically, it can be a worker node, which is part of a bigger cluster, where the control plane of your cluster can either be in the infrastructure edge, or it can be at the cloud. So in general, you can have a combination. Basically, you can have a control plane in the cloud, and then your device edge at the edge, or you can have a hierarchical infrastructure. Basically, your cloud manage your infrastructure edge, and then your infrastructure edge manage further the device edge. So in summary, as I mentioned, there are 3 kinds of architectural approaches. We listed out some reference architecture. For example, you all heard about the Rancher K3s. In our mind, that's the way like you run a whole cluster at the edge. It's lightweight, and then you can, as an IT admin, you can manage your resources and scheduling your applications there. The second one, the reference architecture, is KubeEdge, which is the one I'm currently leading. So the concept for KubeEdge is your control plane is at the cloud, but your worker node is at the edge. So with it, you can have a single pane of glass. Then you can manage all your resources. That's the second one. How about the third one? The third one is the hierarchical, so that it's similar to the federation concept. Basically, your control plane is on the cloud, and then in the middle, you probably have another layer of control plane, which is the infrastructure edge. From that perspective, we see Virtual Kubernetes is an open source project which can meet this need. So next, I'd like to do some comparison among all those 3 architectures and see what are the pros and cons and what are the scenarios are better fit for all those 3 architectures. Then before that, before we drill down, let's look at the current Kubernetes cluster in the data center. So you have multiple nodes talking to a master node. And then your kubelet on the node has a long connection with the worker node. So assuming the network connection is very reliable. Okay, and then also like for the current Kubernetes, the scalability support is up to 5,000 nodes, which means the bandwidth is to that extent. Okay, and then the third one would be when kubelet talks to the master, it watches all the pods on the control plane. And then once the metadata flow down to that specific node, it figure out what are the pods bounded to this node, and then it will call Docker to start the application. So this is the current data center Kubernetes solution. Then let's see, what about, let's say, K3s? What's the requirement to run a Kubernetes cluster at edge? You probably want to think about, at your edge, you might only have a single machine, right? So in that case, you don't want to spend a lot of resources to deploy your control plane. So we want to have a lightweight control plane and a lightweight agent. So I think from that perspective, the K3s can be a reference architecture you can use. And yeah, so basically K3s, for the control plane, it uses SQLite rather than etcd. And then from a kubelet perspective, K3s wrote their own agent and removed a lot of redundant, like unnecessary code. For example, Docker shim as part of the kubelet, which make kubelet really heavy. So let's see about KubeEdge. KubeEdge, as I mentioned, it has the cloud part and then the agent part. For the cloud part, besides the current Kubernetes components, it added 2 components. One is called controller, the other is a cloud hub. And then on the agent side, there are a bunch of components. Just to want to mention, for the KubeEdge agent, at runtime, the memory footprint is only 10 meg. So the benefit of the KubeEdge is you can have a cluster with worker node in the data center, and also you can have worker node on the edge. But on the cloud, you basically have a single pane, a glass of pane to manage your node on the cloud as well as the node on the edge without knowing where those worker node is located. And then you also benefit from the lightweight agent. And then the third thing I want to mention is KubeEdge addresses the network disconnectivity issues. So if you're interested in next 1 hour, I have a deep dive session talking about more in detail about KubeEdge. So the third approach will be the hierarchical. So hierarchical meaning you have a control plane on the cloud. And then you have an infrastructure edge, which is a cluster at the edge. And then your infrastructure edge node manage further a lot of worker nodes. So then let's see, virtual kubelet can be a reference architecture because behind the virtual kubelet, you can have a cluster. For example, in the data center, it can be Azure cluster or Fargate like AWS. But for the hierarchical IoT edge scenario, it can be an Azure IoT edge. So that's another architectural solution. So in summary, I have a table listed here, when to use and where to use. So if you want to have a single glass of pane and really lightweight of control plane, then you can think of KubeEdge, where you have your control plane in the cloud and then your worker node at the edge. But on the other hand, if you want to have strong autonomy of resource scheduling, you can consider K3S. But the challenge for running a cluster at the edge is you don't have a central management of all those clusters. That's come to the third option is like, if you have multiple clusters run at the edge, then you would need to think about a hierarchical solution. So basically, that's what I have.
Thanks, Cindy. So I'm going to move on to some of the unique challenges faced when you attempt to run IoT and edge use cases using Kubernetes. There are 3 categories of challenges here. How do you manage your nodes and clusters out at the edge? How do you manage the infrastructure, the control plane, and the data plane, the interconnects between these apps running at the edge? When I say there's a challenge here, for example, this might involve 2 leaf nodes needing to send things to one another, but it isn't necessarily attractive to hairpin that network traffic all the way back to a central cloud. Some of the issues very unique to the edge compared to understand that Kubernetes architecture was originally based on Google's Borg and a public cloud scenario where you had a huge number of resources with different classes of workloads like batch jobs, which were potentially expendable. Your resources at the edge locations are typically constrained by power, physical size, cost, and they're really not necessarily comparable to what you've got in a public cloud or a large on-prem data center. You've also got the network limitations, the challenge of completely unattended operation at these remote locations, as well as physical security. And we're going to get into these things in detail later in the presentation today. With regard to network, some of these challenges don't necessarily have solutions, or certainly not solutions within Kubernetes itself. They might involve using external tools, and some of them are more like situations involving triage, where if you're just going to have guaranteed periodic network outages, you want to have ways to live with them. We'll get into a deep dive of what you can do about it. First of all, we'll talk about resources. What I mean by a limited number of nodes at the edge, you might have one node, you might have two, you might have three. You're unlikely to have rack after rack. There's no bursting when this comes along. I mean, even if you're in a large public data center and you view it longer term, you can probably order new servers and have them delivered within a day or a week. Out at these edge locations where you don't have IT personnel, that might not be an option. Your workloads may have a wide range of priorities, and there's a need, whether you appreciate it or not at first, for doing triage on these. Likewise, your network capacity is limited, variable, subject to outage. And I'm going to go in now to some examples of what to do, or in this case, what not to do. Yeah, if you're a rookie to Kubernetes, you often go to these workshops, see these examples that show you how simple it is to deploy a containerized app, a pod, and they'll often, the fact is when you go into a pod specification, or in this case a deployment, there are a lot of things that are technically optional and you can leave out, and when you go to that intro session to make this thing quick and easy, they will leave it out. In this example, I hope you can read that in the back, but there's a resources space in this pod spec, and things work perfectly well when you leave that out. What goes there, if you choose to fill out the resources section, is a declaration of how many CPU cores you'd expect to use, how much memory you'd expect to use, and if you choose to leave this out, after your pod gets deployed, your pod could experience anything from resource starvation, one pod negatively affecting another, basically being a noisy neighbor on whatever worker node this got deployed on. And when this happens, when resources run out, let's suppose you get an out of memory condition, if you don't declare any usage or any priorities, this is completely random behavior. Who's going to be killed first if every workload you're running is like this? It's completely unpredictable. Is this likely to be okay? I'm guessing no. I'm guessing that some of the things you're running at the edge are more important than others, and you might have distinct preferences for what might happen. The other benefit is sometimes software isn't bug-free, and if you make a declaration of memory usage and something happens to be suffering a memory leak, it potentially will be killed and restarted, and that's probably a better scenario than just having this thing randomly kill somebody, perhaps an innocent container or pod. What can we do about this? Well, first, let's look at where all these pieces are. It actually is fairly complex in the moving parts, and this is the simplified view, but you start with your pod specification done by the developer. Kubernetes puts the pods that are ready to be run or deployed into a scheduling funnel. There's an admission control process, potentially if you manage to declare it with priority, where some jobs in the queue are able to leapfrog ahead of others, but if you don't indicate the preferences, the Kubernetes scheduler has no idea that you might have these, and it is just first come, first serves. Goes to scheduling, which determines what node it runs on, and it takes into account the resources on the nodes you've got. It might be one in Edge, but it could be more. And if you declared what you need, it can do the right thing with regard to placement. Finally, once this thing is running, the kubelet is responsible for actual enforcement. In other words, I declared I need X amount of memory, but I went way over there and we're out of memory, and somebody needs to be clubbed on the head and taken out. This is a deeper dive. It's really the same things going on that first aerial view, but it goes into greater detail of where some of this takes place. The pod manifest, admission control, moving on to the scheduler, the kubelet. The container runtime gets a bite at this process, and finally, some of these enforcement mechanisms happen inside the Linux kernel. In some of these cases, like out of memory resource, there are actually two places that potentially enforce things. And well, let me go back here. I want to make sure I point out that this is a session covering the broad subject of IoT and Edge on Kubernetes, but there was a really great presentation a year ago at KubeCon in Copenhagen. There's a link there. We'll give you a link to this deck after, but go there and it goes into great session length detail on how all of this works. But I think when you run this as Edge, you need to get yourself familiar with this kind of detail in order to do the right thing. So full specs are always going to be better. You've got two forms of specs. There's something called prod priority and preemption, and this indicates to Kubernetes the importance of a pod relative to other pods. And if you try to schedule or run a pod that has been declared as more important than you've got now, but the resources are fully occupied, something called prevention occurs, which will evict the lowest priority pod. This also potentially affects the order of pod scheduling. So if a number of pods are scheduled and one is higher priority than the other, it isn't necessarily first come, first gets to run. One of higher priority can jump ahead in the line. If you have no specification, there is a mechanism to have a global default, and if you don't specify that, then your pod priority for everything is none, is 0, which means everything is the same, which means it's random. And you really shouldn't do that. You really want to take the effort to give Kubernetes a clue as to what you want to have happen. Orthogonal to this, there's something called class of service. And every workload is going to fall into one of 3 classes of service: guaranteed, burstable, or best efforts. The way to get into the guaranteed class is that every single container in your pod has to have a spec for your memory and CPU consumption, both what's called a limit and request. And like I say, go to that Michael Gash presentation to understand what this is. That's worthy of a whole session itself. But specify everything for every container in every pod you got, and you'll fall into the guaranteed class. And if you have a guaranteed pod, and some of them, you really should put all of them with these specs, but if you don't, some of them have fully specified things, they actually will get a higher class of service and they'll get preferential treatment. If you only specify part of these specs, say you have a pod and I gave specs for one container in the pod, but 2 more containers are sitting there with none of these specified, you fall into the burstable category, leave everything else, everything off, and you get best efforts. And these determine which pod gets killed first when you're out of resource. Understand that Kubernetes itself is monitoring this, but on a very slow control loop measured in minutes typically. The Linux kernel is there, and if Kubernetes is too slow and the Linux kernel determines that the Linux OS is out of memory, it can independently kill something. It has no knowledge of these classes of services, so that results in the random behavior. Network capacity is similar to the resources I talked about a minute ago covered allocations of CPU and memory, but network is another critical resource, and it can be limited. It can be, you see the speed test here, asymmetrical, where the up versus down isn't necessarily uniform, and different workloads are likely to have different priorities and behavior. And this means that you should have different policies. Just like the resources, it is entirely possible, but probably not smart, to ignore your option of defining network policies and just go out there and get random behavior. But with Kubernetes, you have the option of creating these resources called network policies, and they deal with things like what traffic is allowed. By default, every pod is going to be able to communicate with every other pod, but that more than likely is kind of a looser security policy than you'd like to have, can potentially, when things go wrong, produce noisy neighbor problems and just be kind of a bad day. I will caution you that Kubernetes, if you didn't already know this, the networking layer is implemented as a plugin. So some of these examples I'm about to give, some of these plugins may not have all the options, and others are very rich, and maybe even have sidebar options for implementing network security policies and observability. But I'm just going to give you one example to point out that it's important to do this. So when you define a policy, that what's going to go on is based on source and destination IP addresses and ports. And there's an example here defining limits on the ingress, and you can do egress as well if you have the plugin that would support this kind of option. And probably if you're doing Edge and IoT, you need to be on one of these network layers that give you all of these options. Once you've made these declarations, understand that the actual enforcement of your preferences is going to be taking place at multiple levels. It starts with the pod bandwidth annotations, and the prior slide covered restricting who gets to talk to who, but there is something called a bandwidth plugin that may be available if you choose the right network layer that can, in addition to specifying who's allowed to talk to what, you get to allocate bandwidth caps on egress and ingress. This is implemented by the traffic control system in the Linux operating system, and under that, the Linux network namespace comes into play. This is an example of what you can and should do on a pod spec, where in this example, I've called out a spec for ingress bandwidth and egress bandwidth. So at this point, I think Cindy and I talked a little faster than we expected. It's a good thing because we'll leave plenty of time for this. So if you want to take a break, we can do it now. We're going to ask you to divide up. In other words, get up out of your seat, and we'll reseat by these use cases. And even if you don't need a break right now, you get to meet the other people who are interested in the same use case you have. Can you guys grab those signs there and maybe take one to a different corner of the rooms to help this take place? So if you like, go step out into the hall, but come back in 5 minutes. We're going to resume this, but feel free to chat with your peers for the next 5 minutes and separate yourself by these use cases. The use cases are remote office and retail. So this would be at KubeCon Seattle. An example of this remote office retail would be the Chick-fil-A sandwich chain. Had a proof of concept they talked about of standing up a 3-node Kubernetes in every fast food outlet. I think something like bank branch offices or retail stores would fall into that use case. The second use case, sensor data collection analytics, that would be grabbing sensors, perhaps doing some filtering of them before they get published up to a public cloud. I'd also declare that things like video data collection with a little processing, we'll call it that use case. Physical device control would be industrial automation, where you've got sensors that are running tight control loops that need low latency. If you're in that, look who's ever holding up that sign. There are people doing gaming out at the edge where, for best experience in the game, they're trying to run workloads closer to the actual participants in the game. And then finally, telco edge cloud, where there are telcos that are interested potentially in using Kubernetes to manage things running in cell towers or
legacy landline switching offices, and that would be that use case. If you're in the other, I don't know, come up and sit in the front row. So let's reseat in 5-minute break. So I've got 2:30, so at 2:35, we'll start talking about data plane.
So let's continue. So at the beginning of the presentation, we said that we usually have like a 3 common challenges when it comes to the edge computing, right? So infrastructure challenges, how do we put our compute resources at the edge sites? Then we talk a lot about the control plane challenges. So how do we then schedule our workloads to these compute resources? But something I want to talk a little bit now is the data plane challenges. So once our workloads are successfully deployed in a something like a very distributed infrastructure like this, how do we communicate between these services, and how these services communicate with the central clouds, how they can possibly communicate between themselves? And it's on the first look looks like a very complex problem, and the first instinct to everybody is to try to solve this on the infrastructure level, on the L2, L3 levels, trying to put a lot of VPNs everywhere, try to use DNS to resolve services and do the discovery. But in a fairly complex network, it quickly becomes very, very challenging. So that's one of the solution for that is to go up, go on the application level, use some tools that have been around for a while and can be done to solve some of these problems. One of those tools, so just one of the solutions, is AMQP 1.0 protocol. Which is basically a messaging protocol which supports a lot of features. So first thing is to say is that AMQP is a very loaded term. It has a lot of history and it changed over time. So once people first hear about AMQP, the first association is RabbitMQ and the brokers. But AMQP 1.0 is a completely different kind of protocol. I know that it should have been called differently, but this is where we are today. One of the major features of AMQP 1.0, which makes it a good fit for solving some of these challenges, is that it's a pure peer-to-peer protocol, meaning that it doesn't assume that there's like a client-server communication or the broker in between. Of course, you can implement those, but you can implement all kind of different communication patterns like multicast or fan out or request response. So just to give you a quick idea of these different kind of communication patterns, this is what we usually call direct messaging, right? So we have 2 endpoints. One is the producer of the message, one is the consumer of the message. Producers send the message directly to the client. The client accepts the message, and that delivery is done, right? So think about it is like HTTP, where you have like a request direct response. That's like a direct communication, right? But when you talk to people about messaging, everybody assumes a message broker, message queue in between. And this is completely different kind of communication pattern. And you can see from this diagram that you here actually have 2 contracts between in the whole delivery of the message. So first the producer sends the message to the broker owns that message at some point, and then the producer is done, right? And it's the job of the broker to send that message to one or multiple consumers, depending on the semantic of that particular communication that's going on, right? But because of the symmetric property of the AMQP, we were able to develop a new component, which we call the message router. And if you think about message router, it's think about IP router, right, for the IP addresses, but only on the AMQP level, on the level of the messages. And what that means in particular, so what's the difference between the broker store and forward messaging or the direct messaging with the router is that in this case, router never owns the message. It just routes the necessary packets to be able to achieve like a pub sub or point-to-point communication between the different endpoints that are communicated, connected to the single router. All this is currently implemented in a couple of components upstream. We have Apache MQ Artemis, which is AMQP 1.0 message broker, not just AMQP 1.0, but it serves that purpose very well. We have Apache QP dispatch router, which we'll see in action a little bit later, which implements this routing component in the system. And we have Apache Qpid Proton project, which is basically an umbrella project for all kind of AMQP clients you may wish to connect to this kind of network. So this is just the basic components and basic theory behind it. But now things become a little bit more interesting, because if you go back to the edge kind of deployment section, the nice thing about the routers is that they can form the very complex networks themselves. So the routers themselves have ability of auto-discovering the other routers, and they can provide a complex network over which we can send messages in a very, very distributed geographical area, for example. So there's a lot of different use cases. One that I always like to point out, which is a very important for if you go back to the origin of this story. So how we're gonna solve all these edge challenges. So if you take a look at this picture, so this is how we can, for example, enable edge-to-edge communication without with two things to notice. First thing, you can see here that edge nodes here doesn't have any incoming traffic, incoming TCP connections here. So the points of these arrows shows that the routers that are hosted on the edge sites are connected via TCP connections to the router in the cloud, right? But once these connections is established on the TCP level, the full-blown duplex AMQP flow can go through these connections on that layer, right? So the service A simply needs to communicate to the service C on the AMQP level, addressing, saying like service C wants to consume messages from the address C, and service, so that information will be forwarded to the router's network, and the router here will know that. And it will know that for the message sent on the address C, it needs to send that message first to router B, and the router B will know how to forward that message further on through the network, right? And with this kind of architecture, we solve two problems. So first, there's no need for a VPN to get to this, and the second one is that. Is that all addressing is done purely on the L7 address space. So there's no need to any kind of DNS resolutions in the process. I'll just go quickly because I'm using a lot of times. So with this, we can then do like a point-to-point flows through the network completely independently. We can implement a very efficient multicast to the system, sending one message to a lot of consumers through the system. And also these routers implement the best path optimization routes. So they will try to find the optimal path of the message to flow through the system. But if something goes wrong, the alternate path will be available there. And when the original connection comes back, we'll have everything back to normal. So right now I would like to demo this a little bit. So let's see how that's gonna work out. So
he's actually going to show a live multi-cloud demo that is talking to his laptop as well.
until unmirror this. No, I need to mirror, yeah. It's good. So what I want to show here is a little demo that we have these 4 first tabs is basically 4 physically different OpenShift clusters, right? So this first one is in the private server. The other one is the AWS instance, which ACQ instance hosting the OpenShift cluster, and these 2 represents my 2 clouds, which are interconnected. We'll see a little bit later. And then we have two more clusters. This one is behind the corporate firewall, and this one is actually running on this laptop on the conference Wi-Fi in the mini shift. And these 2 are representing my 2 edges. So I must say, like, I use different clusters just to show that this work in this environment, completely physically different clusters, but it can be used on the device's edge as well. So it doesn't need to be the whole cluster to run the router, right? You can run it on a single node, on different nodes. So this is just to show things. And this is how the dispatch router console looks like. So this little white thingy here is actually our console connected to the cloud one. One of the nodes in the Cloud One. How we set up this is that we have two routers per cloud, just to have this high availability feature, and you can see that they're interconnected, so they form like a nice high availability thing there, right? And we have these 2 things here, which are actually these 2 edges running on the 2 different nodes. So first taking point here is that you can see how routers can discover themselves, and even if this console is connected only to a single cloud, we can visualize the whole topology of the whole network of the routers going on here. So next we have these yellow things are the services. I have 2 very simple types of services here. So and we will demonstrate like RPC traffic. So trying to do, a command and receive a control. So we have really 2 simple services. One is called upper, and other is called reverse, right? So one will receive the text, uppercase the text, and other will reverse the text. Okay, so that's as easy as it gets. And we gave the colors to each of these instances of the services running everywhere, just to be able to visualize physically where the responses are coming from. So that's the whole idea. And this little guy here is the client. It's basically one single page here, which gonna use to demonstrate these calls. So there's an address call all here, and if I send a message to all, I should receive the response from all the services running all over the place, right? So, and just imagine this. So this is I'm calling this from the. I think this client is actually connected to the AWS instance of the OpenShift, and it called the service running on the mini shift on my laptop over the conference Wi-Fi without any VPNs or firewalls or DNSs. So all the layering and all the routing was done on the AMQP level. We can also do basically we can do point-to-point, which message will be sent to a single instance of a single service, and it will try the closest service to the caller to instantiate that. So there's a lot of things more we can do with this, but I don't know how I'm on time at this point.
2 minutes if you need it.
2 minutes. Nice. So I have let me clear this. We have also a load gen service, which I can start. I want to show you just one more thing. Okay. So now I can call. So load gen, as the name suggests, try to generate some load, right? And this load gen service is running at this node at this particular cloud, right? So if I generate a very low load here, what I want to show you is that everything, all the load will be handled by the service running on that particular node as well. So no traffic will leave the single node. So we will handle all the requests locally. So let's hope it will work. So let me start, and then if we get the stats from it, we see that all the requests are handled by the red instance of the service, which is exactly what we wanted. That's the instance running on the same node, on the same cluster where the load gen service is running, right? So I need to stop this now. Okay, bear with me for a second. Okay, stopped, and I will instruct this service to start to generate much more load here now. And if I take a look what's going on, we'll see that at this point, sorry if I'm clicking too fast, but it will all come clear now. We see that at this point, the red service, and that's how the whole network is settled, because there is a flow control implied in all these routes. We can see that with this particular configuration, it's set that the red service will only get a part of the load, and then the rest of the load will be offloaded to the other sites, to the services being located on the other basically clusters. So that's what I wanted to show you today regarding this. So maybe now we can go back to the presentation, if I can find the PowerPoint. Yeah. All this is done with the.
Looks good.
With the operator for the QP dispatch router, and there's so this demo is in the rough shape still, right? We're working on it. So you can find the source here and you can play it around, but what certainly we'll do in the future, try to document it more and try to present it more so that more people can play with it, and instead of writing these simpler services, try to put it in the proper context of the edge computing.
Okay,
so
thank you.
Yeah.
Hilton, if you can do this in 20 minutes, we have 5 minutes left for Q&A.
Thank you.
Okay. Great. So, I can't express enough affection for that protocol, AMQP. That is fantastic stuff. By the way, if anyone wants to continue the group discussions that we were having on the break there, because it seemed pretty lively, after this session, we're all up for being available outside of the conference room to continue those discussions. So this is a topic that would normally be, a talk in itself, and so I'm going to do my best to bring it together in the final 20 minutes. There's a joke that I like to tell. How many of you have heard this before? The S in IoT stands for security. Does anybody have? And if that's new to you, feel free to reuse it. It's truth. It's true though. So. The gist of security at the edge is that it's a completely separate environment. It can't be added as an afterthought. So if security is normally the sort of thing that you put your system through as a final check, a penetration test or whatever, and say, okay, it works, now let's get the security in place and launch it, this at the edge is going to kill you. And that's because the edge environment is very different. So you want to be designing security into the edge infrastructure from the start. And so the best way to do that is in this Kubernetes IoT Edge working group, we have begun to assemble and are actually nearing completion of a white paper that exposes the challenges of security at the edge. The reason we start with this is until we have identified everything that we need to overcome at the edge in terms of security, then we won't really be able to assemble the right architectural approaches to fixing it. And too often we have piecemeal security solutions that we think have solved the issue, only to find out that in combination with everything else, it's just one tiny piece and the whole thing is not yet secure. So expose the problems first, and then we can know what solutions we need to be designing. So there are some key differences about the edge environment that make security a particular challenge. We just saw an example of diverse networks. Some things are behind firewall. Some things are over VPN. VPN's not a good idea, by the way, usually at the edge, but some things are on cellular. Some things are through 3 different NAT layers because they're inside an advanced manufacturing facility. And you have to try to bring all of those things together, but still in some way represent the identities of the things in a way that allows you to do data flow control and so on. Also, there's no guarantees of continuous power. So out at the edge, you might have things that are running on battery or solar charge battery. And when things go offline, the perfect opportunity to hack is then, because as it comes back up, things look strange anyway, and you might even be fed some initial commands to allow you back on a network. That's a great time to be present and trying to get access to a system. And you have intermittent connectivity. So if you can guarantee that everything's flowing all the time over a high-speed LAN, then you can maybe watch the traffic. But what if the traffic comes in bursts or is offline for 2 days in a row because of a cell tower outage or there's a dust storm and so on? You have to take these things into account. And at the edge, you have direct physical access to hardware. So how many of you believe that if you wanted to go and attach a keyboard and a mouse to someone's cloud server, that you would be able to find where it is and get in and do this? Anybody feel like you are up for this challenge? It's not going to happen. How many of you feel that you could go and put a ladder on a light pole and access a camera that's part of a smart city deploy? Anybody figure you could do that if there's no police around? Yeah, it's a completely different environment. We have to take this into account. The hardware at the edge is heterogeneous. So it's really easy to buy, hundreds or thousands of servers to go in your data center, all from the same supplier, all with the same spec. But at the edge, you have a mix and match. You have different machines. You have boards that have been in place for dozens of years. And you would like to access those boards over serial port with some new IoT gateway. That IoT gateway that you bought is different than the one that was bought 2 years ago, and so on and so forth. And we have a lot of non-TCP IP communication. Anybody ever program with Bluetooth? Has anybody ever done any Bluetooth development? Bluetooth is non-TCP IP and it's short range. Anybody use LoRaWAN for IoT? That's good stuff, great long range, decent bit rate, not TCP IP. And so then you'll also have multiple vendors. They're very different than racking out your data center. And you'll need to handle security in offline mode. So a lot of times we take a look, we have some kind of advanced AI-based security traffic monitoring in the cloud. Let's take a look at what's coming into our data center and we start to sniff out things that don't quite look right. But at the edge, you actually need to be able to handle security down on single or multiple node level off of the cloud connection. And at the edge, you have very low latency locally. This is one of the advantages of the edge, but you have a higher latency to the cloud and back. And so you have to take into consideration that you might not get answers as fast as you want. So there's kind of a summary or an overview of the types of security challenges at the edge. Not said yet to be complete, but complete enough for us to be talking about it. And so the gist of it is you have to trust the edge hardware. This is the hardware that's running your edge computing. You have to be able to trust the devices connected to that edge hardware. You have to find some way to deal with operating systems at the edge and the fact that they're complex beasts. You have network concerns. And then, of course, now say that all of those things are in place. Edge microservices themselves pose some new challenges, and we're going to talk about how to, or some of the things that we've exposed around edge microservices. So starting with trusting the edge hardware. So I already mentioned that physical security is not guaranteed at the edge. In fact, I would say physical security is actually very difficult at the edge. And there have already been plenty of hack attacks. I've suffered one myself. I was an IoT advisor to the city of San Francisco, and there were some incidents that occurred a number of years ago, really opened my eyes. You have people going out with screwdrivers and wrenches and saying, I think I can get at that box. What do I think I could do with it if I got it? So the hardware root of trust is a starting point. For a lot of people, a TPM 2.0 module is kind of the de facto hardware root of trust solution. If I've got that, then everything that's riding on top of that hardware is said to be good. That's not actually true because hardware root of trust is just a starting point. This basically tells you that the board that you're operating on is the board you think it is and looks to be still in the same condition that you last trusted it in. But building on top of that, that's like the basement foundation of a house, right? What's built on top of that still needs to be good quality, but you do have a solid foundation. So what about the condition of the hardware? So if I have some orchestration that's happening with Eclipse IO Fog and it says, within these GPS coordinates, I would allow the following microservices. So it's some center point and then some radius. A great way to get microservices issued to your edge hardware that's not supposed to be allowed would be to spoof the location. So even if GPS coordinates are normally thought of as something that's fairly safe to have transferred, in an insecure way, because it's just a couple of data points, what if that is actually used to make decisions about what software is supposed to run where? That's actually a really great technique for getting software issued to your boxes to make it look like you're inside some trusted circle, and when you're really not. And so then attached devices start to become much more of a problem at the edge. So what do you do if your edge hardware node, so an IoT gateway, all of a sudden has a USB flash drive attached to it? That's usually a warning sign, and if it was your laptop, you would be very concerned because who's getting up to your laptop and plugging in their USB drive? But for an IoT gateway that's at a remote oil pump, this might be something that you're never aware of. So you're going to need to do some kind of detection of what attached devices are present and what condition they're in, and are they on the trusted list, because no one's going to be there to watch it, not like there is with your phone or your laptop, which you won't let out of your hands. And so if you do have an indication of compromise, like something like an open case on an edge compute node, right? There's a lot of case detection systems, right? It can tell that somebody has opened the box. But what do you do then? If you just go power off, then maybe they'll just take the thing off the wall, take it home, and get the data when they get home. What you really want to do is, if at all possible, find some way, so your challenge is, find some way to detect that there's compromise and react to it in a way that saves you. Can I wipe the data? Can I wipe off the microservice images? These would be good things. Can I make sure that everything's encrypted, and then therefore, even if they get the hard drive, it's not a problem? Okay, great, but then I need to have some monitoring of the whole system. And so what about authenticity of the hardware? So in some cases, you have hardware that you trust, but then you come to find out later that there's security flaws in the hardware itself. Possibly even some way that someone's doing remote monitoring of the hardware and you weren't aware of it. So know the sources of your hardware and know that what you're putting out in the field not only has a TPM 2.0 module, but that all of the setup on the board is what you intended to pay for, and there's nothing there that is waiting for a BIOS update through a backdoor or anything like that. So just be careful of supply. Trusting connected devices gets really tricky. So these inexpensive battery-powered sensors, the kind that you'd put 10,000 in a warehouse, they don't tend to come with identities the same way that like a main board of a computer does. So whereas a rack server is going to have all the software identity stack, with a little battery-powered device, how do you know which one is which, and how do you trust? And that being said, if you have 10,000 of them, who is going to assign the identities to the deploy? That's a lot of numbers, and where are they going to plug them into for you to say, oh, that ID belongs, that ID doesn't belong? So you have to consider the cost and the labor involved in getting these systems deployed. So if there's data flowing, you want to protect that, possibly encrypt it as near as possible to the source, but what about commands going back out? So some really interesting commands are shut the water valve off, or open the gate to the warehouse, which is a mostly automated facility. If I can issue that command remotely, once I figure out how to get into the system, then I can basically just line somebody up and say, okay, you're ready to steal in 5, 4, 3, 2, 1, let me issue the command, opens the gate, and we're done. So who's watching what commands flow? That's a very funny place. You might not have any monitoring of the traffic, and yet then somebody just happens to get on the Wi-Fi network, issue the command, and you're done. Device management is actually a backdoor. So think about it this way. If you have a device cloud, and in that device cloud you're saying, of all my IoT devices, several hundred of them, this is the battery life that's remaining, this is the network address of the device, this is the firmware version I've got, and you use that information to make some decisions, such as, oh, we're almost out of battery here, Let's go ahead and move the workload over to where we're getting sensors that have more data coming in because the battery is still alive. If somebody spoofs that information, then you can force decisions on the back end. And a lot of the device management API systems or cloud systems, they're open. All you really need is an API key, and you can get that off of any one device. So steal a device, and you steal a way to report the data in falsely, decisions start getting made, and nobody's any the wiser. So the operating system, this complex thing. So who's heard of Secure Boot before? Who uses Secure Boot in any of your deploys? It's tough. Secure Boot is a hard thing to get right because basically it says, I'm on some hardware that hopefully I trust, and I'm going to execute the boot sequence like this, and I'm going to check that I'm only loading the drivers that I'm supposed to load, and I'm only running the binaries I'm supposed to run, and I'm only opening the network configuration I'm supposed to open. And then you're done. You basically report, I securely booted. What happens after boot? So then you get some software that decided to give itself an update, and you trusted that software, you installed it, but now the update it's got is doing something funny. Secure Boot won't save you. So Secure Boot is yet another step. So hardware root of trust, Secure Boot, these are the first two layers. What comes after that? You have to know what's running, and you have to know that the thing that's running is pure. So some attestation of what's happening on the edge node, and you need to continually monitor this because when you're in the manufacturing facility and you're kind of getting everything ready and all of your binaries are loaded, it looks fine. It's when you go out to the field that you'll have a change. So it's not enough to say that the image looks fine. It's going to change afterward if you're actually going to get hacked. So constantly monitor. So this one is kind of a pet peeve of mine and something I like to point out a lot. So if you have a private key and you put it into an edge device, and that's meant to be the identity, right? So it can attest, I am this thing. What happens if someone gets a hold of that device and they're able to get a hold of that private key? This is essentially like taking your house keys, putting them on a park bench, and you might as well put an address tag on it too that says where you live. Because you have now given yourself a false sense of trust, and you've given the keys to your kingdom out into the world. What's the answer to this? It's actually really challenging. Something related to using keys and asymmetric key pairs, but maybe giving them out when you know the device or the edge node is trusted already, so something that's more dynamic. I know that flashing fixed private keys into edge nodes is very dangerous. That's for sure. And so component firmware vulnerabilities is also a problem. So your OS is running, and you're talking to the serial ATA chipset there. Who made that? Does it have vulnerabilities? Are you riding on this for all of your edge deploy? Probably not. You probably have 10, 20 different vendors based on the variety of boards you have. How are you going to check for security vulnerabilities in all of these chipset firmware versions that are on the board? It just starts to become a nightmare. So much of a nightmare, in fact, that some organizations in the United States, the NSA, for example, requires the authority to turn off all of the security features baked into all of the components of the board. And this is so that they can override and say, well, at least we have visibility instead of trusting some of the stuff that's been put out there that might have flaws in it. Hopefully this is all getting you scared, right? Because it gets me scared. And so what about security updates of the OS? The security updates are great until somebody gets in the middle of them. So this is a golden opportunity to cause problems. Also, are you doing security updates of your edge nodes? In some cases, you put a pump controller out in the oil field, and once you put it out there, you want to conserve bandwidth. Maybe the bandwidth that you are paying for is on satellite, very expensive, and you say, patches recommended for Ubuntu. Nah, that's like a lot of money. We'll do it next week, right? And this is because you're trying to make a cost-benefit analysis, right, of consuming bandwidth. And so then whatever happens on the OS usually produces an audit trail and some logs. That's a great place for people to hack. It's also something that's typically missing from the edge backup. If I can't get access to the audit trail or the logs, then I'll never know what happened out there. Something has to take care of these things and treat them like data, because you're not guaranteed protection, right? No physical protection of your edge node, so something has to treat log files as first-class citizens now. So on the network, another pet peeve of mine is open ports at the edge. So there have been some hack attacks executed against energy grid systems where somebody really just kind of rolls up near the transformer facility. So you've got these kind of fenced off areas outside cities where you do power transformation. And there have been hack attacks where people roll up, start scanning for wireless network connections that are available, especially SCADA, and then they just begin to say, well, based on what I'm seeing, there's actually an open socket here that I can talk to. I'm gonna issue a couple of bytes commands and see if I can get it to feed me back some data or do something. And it's basically just sitting open because nobody thought that anybody would ever be out there with a laptop and there's different wireless adapters trying to do these things, but it's starting to happen. And fixed VPNs are like fixed private keys. So you definitely do not want to put edge hardware out there that contains VPN credentials that if somebody gets access to the edge hardware, they can get on your VPN. Because that's like saying, I have a warehouse, and I have a data center, and I have a retail store. Hack any one of them, and you get the other two for free. Right? We don't want this scenario. Network access control. So identities on the network are pretty easy to establish, and in a fixed environment, that's good. At the edge, you have things roll on and roll off. If a truck pulls up to my warehousing facility and it wants to join my network here and start doing some edge compute data sharing, you want to dynamically give it access. But then you're not going to have a network engineer on standby at all times saying, let's let this identity in. So you tend to open things. That's not the right approach, but you have to think, how can I dynamically check identities? And so then we always talk about verifying what's happening at the edge up in the cloud and saying, like, is that the right device? Did it give me genuine data? What about the edge saying, am I talking to a real control plane? Because we have this notion that the master node is going to be like walled off and protected, but it was a conversation actually happened at the Eclipse booth earlier today. It was really interesting about smart cities. If you get access to the master node, you control the city. This is kind of a future we're heading towards, so think about it. The edge node should say, something changed on that control plane. I'm not liking it. And, I'm just going to go into offline mode until I can get re-verification. That would be a much smarter and better edge. Attacks of the transport layer is very interesting. For Bluetooth, LoRaWAN, all of these local wireless things, if you just blast a bunch of noise, you can often interrupt the transmission and prevent any data coming through. That's a great way to turn off water flow or cause something to overflow or cause fuel line transmission to stop. All stuff that you can do just by blasting white noise. And this is a problem that we don't have a solution for. I can't think of any way you can't radio shield things so much that they don't get interference because then they don't get transmissions. I'm not sure how to solve it. And this is a term that actually came out of a years ago working group that was, I think it was Edgeworx, and it was Cisco, and it was Samsung, and GE. Back when GE Digital was really in the space and more of a thing. And so denial of thing attacks are kind of like this. You have a device, and it's reporting data. Maybe it's a temperature, and it's reporting it over Bluetooth Low Energy. I don't actually have access to the device. And I don't think I'm going to get it because it's actually encrypted data that's transmitting. These are all really good architectural implementations. But I can ask it to connect so many times that it runs out of battery. And so you're basically denying all of the things of the world from participating in the solution. This is something that we don't really have a good solution for. Okay, last section. Did I get the watch from Steve? So when you are running microservices at the edge, you have to make sure that the microservice images are the ones that you intended. There's a lot of solutions for this in the cloud arena, and all we really have to do is make sure that you can do these checks, valid checks at the edge, and do them quickly, or maybe in offline mode. You have API keys and things. Find a way to securely deliver them to the edge instead of having them baked in. What do you do if you have microservices running at the edge that were unauthorized? Is somebody watchdogging? Is there a whitelisting capability? And so if that's not built in, then I could basically deploy microservices just by getting on the edge node, and you might not know. Controlled access to resources means serial ports are available to microservices. Are they available to all? Should they be? What about Wi-Fi connectivity? What about the Bluetooth radio? That should be controlled. Guaranteed remote shutdown. If I'm remote and I'm managing an edge node and I say, okay, repeal, right, I want to turn off these microservices and I'd like to wipe the data because we're decommissioning this IoT gateway or we're decommissioning this video camera that's been taking the video feed and doing AI, I need to know that that stuff's wiped off before I basically consider it no longer part of my edge compute system. and you want to match the right microservices to the right edge hardware. So it's no good if you deploy a microservice that checks employee IDs in a factory and says you can or cannot be in the sector. No good to run that microservice at the edge if it runs in the women's restroom. And so then there's no real control because it's not at the right targeted location. So match the right edge hardware to the right microservices. And the last one is microservices at the edge are great, but they're largely unmonitored. And what happens if you deploy one that just starts sending your data to some back channel? And this happens. People write microservices and they put them out there for free. And say, oh, hey, use this. This is an MQTT, the broker slash, analysis system that will give you a great, Edge IoT system. And you look at it and you're like, well, I don't have access to the source code and I'm not really sure where they're sending all my data. So maybe I should think twice about that. Cool. So the gist of it is, in the end, it's going to require a multitude of approaches. And everybody's going to have to get involved. So what we really need to do now is start thinking security first, question the status quo. So just because it works in cloud and data center doesn't mean it's right for the edge. And just remember, the edge environment is so different that unless you're absolutely certain you've explored all the challenges, you should assume that things aren't yet safe. And then start to get involved that way, asking the right questions before we start giving the right answers. So cool. Steve?
Okay. Thank you, Kilton. That was a great talk. And like he said, I think potentially that talk would be a 90-minute session on its own, done right. Let me wrap up here by pointing out that this session you just attended is being run by this IoT and Edge working group within the Kubernetes project. We have 2 meetings per month. The reason we have 2 is one is done for the convenience of Europe, Eastern Europe, Asia, Japan, the other one for North America. Once you get synced onto the right one of these, and I'm sorry that I've observed that some people join at the wrong time for the wrong 4-week cycle, but look at them here. Take a picture of the top there for that shortened link. You can get this whole deck to find it later. And these are Zoom meetings, interactive. You can come on via camera if you like. And we're trying to organize this with presentations like what you saw today. If you're with some open source project or some vendor, we don't really want to give airtime to commercial sales pitches, but if you've got something particularly open source that you want to present, approach any one of us and we'll put it on the agenda. Likewise, if you're users, and I think some of you got captivated by the experience of breaking up into groups who want to have a meeting focused on your use cases, we'd be willing to do that. And just give us help as to what you'd like. Once you join this group, it's the Kubernetes Community Standard. You don't get to see the full extent of the documentation, the documents, without joining the group, but it's easy to join the group. Join it, you'll get access to the meeting agenda for these, and you're free to simply write in the agenda document and suggest topics to be discussed yourself. We won't guarantee that if we run short for time, it will get in that one, but you'll get yourself in the queue. And we've got some working white papers. Once you join the heading for the group, you can discover all of this stuff. At this point, I think it looks like we hit our deadline. If another speaker walks in the door, we'll take it out in the hallway out of courtesy. But at this point, if anybody's got questions, I think we have an extra mic. I'm not sure where it's at. Okay, so raise your hand. And
my mic if needed.
And then if not, I think we had to break up some of these groups. So if we have no questions, let's reassemble in the hallway, divide it up into those popular groups, and let's get to meet each other. Okay, we've got one. Okay, so we're likely to be able to continue. Any questions, or do you want to go into these focus groups again? Let me know. There's one.
Hi, I wanted that you are more clear about what is the roadmap of this working group. What are you planning to achieve?
So the roadmap for the first 6 months, we try to cover this material for the intro, try to figure out the use cases and things like that. And for the last couple of months, we're basically focusing on what we presented here, so focusing a little bit on security, focusing on the messaging, trying to deep dive into these things. I know on the recent calls, we had a proposal to do some work around verifying the Docker images for the edge nodes and things like that. So it's basically open for now. Yeah.
It's on demand. Okay.
Yeah.
Thank you. Thank you.
Okay, it looks like that's it, but feel free. We'll step out in the hall if somebody wants to chat privately. Certainly the four of us really love this, so we'll hang around. Thank you for coming.
Yeah, quick thing, like at 4 o'clock, 3:55, I have a deep dive session for KubeEdge if you want to learn more.
Oh, you know what we forgot, Cindy? We do have some shirts available.
Oh, yeah.
Certainly offer one to whoever
they're all
asks the question.
medium size. If you're interested, come to me. Yeah.
Thanks for coming, and
Yeah, thank you.